This is a short series of presentations to assist paraglider and hang glider pilots who are studying for their BHPA pilot rating exams. This series is on flight theory and instruments. In this section, we complete the flight theory syllabus and look very briefly at instruments. Polar curves are a technical and mathematical way of expressing the change in glide performance over different airspeeds. All aircraft have a polar curve which shows the rate of descent of the aircraft at different speeds through the air. On the left-hand side, the line turns suddenly down as the descent rate increases precipitately at the point of stall. On the right of the curve, the line starts to gradually veer downwards more steeply as the parasitic drag increases and the glide performance decays. The two axes under which the curve is drawn, a glider is always descending in still air, are airspeed on the horizontal, x, axis, and descent rate, or climb, on the vertical axis. Three different airspeeds can be determined from a glider's polar curve: the stall speed, the speed at which the glider is sinking least fast, known as min sink, and the speed to fly for the most efficient and therefore the furthest glide. To illustrate the polar curve, we can use an example of an identical sailplane flying at one of four different airspeeds in still air. In this illustration, we have the same glider in four different colours. The blue glider is flying the slowest at a speed below minimum sink but just above stall speed. The green glider is flying at a speed which is known as the speed for minimum sink, min sink. The yellow glider is flying at best glide, and the red glider is flying as fast as possible. Assuming they're all left from the same point, after the first minute of flight, we can start to draw the polar curve against the position of our four gliders. And the polar curve predicts that the yellow glider, flying at optimum glide, goes furthest. The green glider, flying at minimum sink, stays in the air the longest. The red glider flew fast and landed around the same time as the glider flying at just above stall speed, but the red glider flew further. The green glider has the lowest sink because it was flying at min sink. It will keep you in the air for the longest time, but won't go quite as far. Meanwhile, the yellow glider has the best glide ratio of all. That means it will glide further in still air than any other glider for a given loss of altitude. A line from the origin, 0 point of the graph, that just touches the polar curve represents the glide path of the yellow glider. Now, if air was always still, that's all we'd need to know about polar curves. Minimum sink speed would keep us in the air for the longest time, and best glide speed would allow us to go the greatest distance. Speed to fly is the speed that results in the flattest glide in both convection and in wind. Speed to fly can be distilled down into these two simple statements: speed up in sink and headwinds, and slow down in lift and tailwinds. We could also plot the same thing against our polar curve. In a 20 meter per second headwind, the polar curve dictates that we fly 20 meters per second faster. And what speed to fly in lift? By setting the origin of the intersecting line below the 0 point on the vertical axis, then the point where the straight black line intersects the polar curve represents the airspeed to choose for best glide in that amount of lift. The red line is the intersecting line which is used when the air is neither lifting or sinking. In this illustration, moving from still air into lift of 0.5 meters per second, it suggests slowing this particular aircraft from around 36 to 20 units of airspeed. The final section of the syllabus asks us to look at altimeters and variometers. These are the typical types of instruments that have been used in free flight from the early days. In recent times, these features are generally integrated into one GPS-enabled instrument. However, to measure airspeed, these instruments need a probe within the airstream to feed data back to the instrument. For our slow-moving aircraft, we are generally content to do without this component of information. Barometric altimeters work on the basis that atmospheric air pressure reduces by 1 millibar for every 30 foot that we rise. This is why it can be important to make yourself aware of the prevailing atmospheric pressure when navigating airspace. Airspace flight levels are defined by barometric pressures. This means that when the sea level barometric pressure is higher than the international standard of 1013.2, then the actual altitude of a flight level is raised by an elevation of 30 feet per millibar. An example would be if atmospheric pressure were 1030, then a flight level would be a higher altitude at by around 500 feet. Most of the modern altimeters we use in our integrated flight instruments these days report our actual altitude using GPS. Variometers detect and then display the rate of change of air pressure outside rather than the absolute air pressure. The faster the ascent, the faster the rate of change of air pressure. If a glider is travelling fast, then slows and converts speed to height, this can confuse air pressure varios, so total energy varios were developed to take account of airspeed. So-called netto or air mass varios accommodate the rising and falling of the air mass and indicate the glider's net lift or sink. This is a term that's rarely, if ever, used these days. So that's all of the syllabus of the BHPA pilot rating exam covered.